Hi class, welcome to exercise 10i, graphs of polynomials. In our lesson today, there's just the one example, that's example 18, sketching cubic graphs. And your pre-learning for this example is questions 1 and 2 in the new book, or question 4 in the old book. Now, as you've seen in previous lessons, just because we've only got the one example, does not mean it's going to be a quick and fast lesson. So this topic brings together all the other topics that we've covered in the block. So buckle up, there'll be a fair bit of work. I'll see you in the introduction. Well, you know me, if we're going to do graphing, I'd like to start with a table. So let's choose some values of x here between -2 and 2. And I'm going to compare x to x squared, x cubed, and x to the 4. So I actually think I need to make a little bit more room there. And let's close off a table. So when x is equal to 1, x squared is equal to 1, x cubed is equal to 1, and x to the 4 is equal to 1, right? And the same for 0. So there's no surprises now. If we were to take 2 and then square it, we'd get 4. Cube it, we get 8. And raise it to the power of 4, we get 16. And of course that means 1 over 2 squared will be a quarter, and cubed will be 1/8, and to the power of 4 it'll be 1/16. And a quarter squared is 1/16, cubed it's 1/64, and to the power of 4 to the power of 4 is 256, so it's 1/256. So I think I can finish closing off the table now. So what's noticeable here is that when x is equal to 1, doesn't matter what power we raise it to, it's always going to be 1. And for the number here 2, the one that we've got that's bigger than 1, as we raise it to bigger powers, it gets bigger and bigger, and quite quickly as well. But these numbers between 1 and 0, as we raise the power, it gets smaller and smaller. So that means that these graphs start to form a shape like this. So I've used the same colors here in GeoGebra, and it should be obvious that this green one here is x, and our orange one here is x to the 4. So it looks like someone's tied a pigtail, doesn't it? As they all pass through 1 there. But if you follow this x to the 4, it shoots off higher past 1, and it sort of flattens out and gets closer to 0 much quicker. And in fact, when I get to 0.2, it almost looks like 0, doesn't it? And cubed is closer again, and squared, well, we've seen squared in our quadratics unit. The ones that are closer to y equals 0, as x gets closer to 0, shoot much faster in an upwards direction past 1. All right, let's have a look at some negative values there. So x squared doesn't matter if it's negative or positive. So all these values here are going to be the same. And that's because a negative times a negative is a positive. And the same is true for x to the 4, because a negative times a negative is positive, times a negative is negative, times a negative is a negative times a negative, and that's positive. Goodness me, that was a mouthful. So that means that the values on the left for x to the 4 are going to be the same as the positive values. If we have a look at x to the 3, let's start with x equal to -1. So -1 times -1 is positive 1, times -1 gives us -1. And what that tells us is that the size of the numbers is going to be the same for our cubic. It's just that they're going to be negative instead of positive. So I could easily fill those in here now. So I've printed out a picture of positive and negative graphs on the negative side as well. And you can see here that x to the 4 is a lot like x squared, except it's actually a little bit flatter at the bottom. And x cubed is like x, it's just not a straight line. It has sort of some curviness to it, but it's going from down to up as x moves from left to right. So this means that odd powers, if they're positive like x and x cubed, well, they have this general shape, and as we move to the left they sort of trail down to minus infinity. And as we move to the right, they move up to positive infinity. And if they were in a negative shape, then minus x and minus x cubed would have this basic shape. And as we move to the left, they move up to positive infinity. And as we move to the right, they go down to negative infinity. Whereas even powers, like x squared, x to the 4, they have that general shape like a quadratic. So as we go to the left, it goes off to positive infinity. But also as we go to the right, it's heading off to positive infinity. And if they were minus x squared or minus x to the 4, then we'd have that negative quadratic type shape that heads off to minus infinity on the left and minus infinity on the right. And this is why we call them odd and even functions. But it doesn't matter what power of x we're dealing with here. The key points on a graph are always x-intercepts, which is just where the polynomial is 0. In other words, y is equal to 0. And this is where our last lesson becomes important, because of course this is the same as solving polynomials. And along with the x-intercepts, we always worry about the y-intercept. And that's simply where x equals 0. In other words, p of 0. Now today, we're focused purely on cubics. So as we saw with some of the solving polynomials in our last lesson, we could have a cubic such as y is equal to x minus a times x minus b times x minus c. And if I was to draw a little graph off to the side here, then our x-intercepts is where y equals 0. And as we saw in our last lesson, using the null factor law, in this case, that would be where x is equal to a, or x is equal to b, or x is equal to c. And I can just quickly mark them on the graph. And of course the y-intercept is where x equals 0. So subbing in x equals 0, our equation there would become y is equal to minus a times minus b times minus c, which is equal to minus abc. So of course it's not clear if minus abc is up here or if it's down here. It's really going to depend on where those x-intercepts are, right? So to have a little example, let's just try y is equal to x plus 1 times x plus 2 times x minus 1. So if I multiply x plus 2 times x minus 1, that becomes x squared plus x minus 2. And of course, we're still multiplying that by x plus 1. And then if I expand that out, I get x cubed plus x squared minus 2x when I multiply everything inside the quadratic by x. And then obviously multiplying it by 1 gives me x squared plus x minus 2. And when I collect like terms, that will give me x cubed plus 2x squared minus x minus 2. So if I was to rewrite out that polynomial in a negative version, then obviously when I expand it, it's going to be the same as the other one, except for negative. And obviously minus 2 and plus 2 here are y-intercepts, because that's what we get when x is 0, okay? All those other x terms disappear. And we can find our x-intercepts here, not forgetting that we take the negative version of that, i.e. it would be minus 1, minus 2, and plus 1. So let's see if those points will tell us all that we need to know about a cubic in this GeoGebra applet. And let me add the link, of course. Alright, we'll see you over there. Alright, so this applet here has been created with these black points, and when you drag them around, it creates a polynomial that fits perfectly into those points. So I'm starting here with x cubed, which you can see in the equation up here. But I want to drag those points into the right place. So we had a y-intercept of minus 2. And automatically you can see we're starting to get some weird shape here. So let's fix up those x-intercepts. And they were minus 2, minus 1, and 1. And sure enough, we see this weird shape here. And while that initial shape was x cubed, this is the shape that always comes to my mind when I think about cubics. And just like 3 points will tell us all we need to know about a quadratic, these 4 points tell us all we need to know about a cubic. Because as you can see, dragging them into their place has created the equation that we had in OneNote. So for this year, being able to point out the y-intercept and the x-intercepts actually does tell us all we need to know about the cubic. The only thing is that we won't know is where are these humps. And as I said, we won't be covering them this year. This is something that you won't know until you do some of the techniques that you're going to learn in methods 1, 2 next year. So hopefully this is all the motivation you need to learn calculus. So if you remember the negative version of this graph, we had exactly the same x-intercepts, we just had a different y-intercept. And looking at the equation, it is exactly the same thing, except the sign has changed for each term. So if I move that y-intercept back, notice the graph looks like a steep linear graph. It might help if I zoom out a little bit. So yes, it does look like a steep linear graph if you ignore this little wiggly bit in the middle. And this is the positive version, so it's going up as we move from left to right. And if I switch back again to the negative version, it looks like a steep negative linear graph. Okay, so this is how I see a cubic in my mind. But once again, let's have a look at the standard cubic graph. So it is just like a linear graph again. This time the curvy bit in the middle isn't so up and down, like it just seems to flatten out. And we really only have one intercept here. So if I switch that all around to the negative version, you can see it's basically the same graph. It's just sort of upside down. I don't know. Now I'm going to switch it to a positive, but with a slightly different intercept. So this is exactly the same as the initial graph. It's just that the intercept is at -1, not 0. And maybe some of you who understand a little bit about Pascal's triangle can see the coefficients in the equation and understand that this is a perfect cube. It's just not x cubed, this is x plus 1 cubed. So we've seen a graph here of 1 intercept, and earlier we were looking at ones with 3 intercepts. I just want to pop back into OneNote to discuss one more possibility. So remember in our last lesson when I spoke about 2 intercepts? And that occurred when we had a square in the equation, like y equals x minus a times x minus b squared. So if we were to try some numbers there, so y equals x plus 1 times x minus 2 squared. To know where all my intercepts are here, I'm going to have to expand it. So we've got x plus 1 times x squared minus 4x plus 4. Simply expanding that square. And I'm going to quickly expand this whole expression. And when we collect like terms, we end up with x cubed minus 3x squared plus 4. So clearly, plus 4 is a y-intercept, i.e. when x is 0, y has to equal 4. And to find out x-intercepts, x plus 1 equals 0 means that x equals minus 1. And x minus 2 equals 0 means x must equal 2. Okay, that doesn't matter that it's in a square, it's just 0 then. So you know we need the 4 points for a cubic, so I need to make up another one. So I'm just going to pick on x equals 3 and just sub that in. And 4 times 1 squared is equal to 4. So my 4 points are going to be x is 0, y is 4. And I've got x is equal to minus 1, then y is 0, and x is equal to 2, then y is 0. And this final point here, I've got x is equal to 3, and y is 4. Alright, let's pop back to OneNote and see what that looks like. Alright, let's move our points around just to where we found them already. So we can move this top one to 3, 4. Wow, that's a line now. We can leave this intercept where it is and move our y-intercept up to 4. And finally, let's move our last point to an x-intercept. So as a reminder, we had an x-intercept at -1 and 2. Our y-intercept was 4, and we had that other point 3, 4. And sure enough, we have 2 intercepts. And we know where that x-intercept equals 2 is related to the square. And so yeah, we've got the round bit there. So do you think that we have 2 intercepts because I've got 2 points on the line and 2 points elsewhere? Or is there something else going on? Well, let's move this intercept at 2 closer to 1. And yes, we've got 3 intercepts now. So clearly, it's all about having that perfect square as a factor inside the cubic. All right, let's go back to OneNote. All right, it's time we had a look at some basic cubic shapes. And you know I love to make tables, but this time we're going to make our tables in GeoGebra using this applet. So this applet allows us to choose the function that we want. As you can see, I've got function written there, and we can plot out the points between the x values of a and b, and it creates this table, which you can see down the bottom. So starting off with x cubed, minus 2 cubed is minus 8, minus 1 cubed is minus 1, 0 goes to 0, 1 goes to 1, and 2 goes to 8. So here are those points marked in on the graph. I've also got the ability here to select lines. So let's imagine we had straight lines between those points. And you know that it's going to be a lot more curvy than this, but this is the basic shape of a perfect cube. And if I switch to minus x cubed, you can see it's the same shape, but y is growing in the opposite direction. Now, if we just zoom in a little bit here, and then increase the amount of steps to 8, I just want to move it up a little bit actually. Having 8 steps here is equivalent to a half step, i.e. you can see it goes from minus 2 to minus 1.5, etc. And already the line is starting to come a little bit more curvy. So if I was to make it now 12 steps and then 24 steps, which is equivalent to taking a step for 1/6, the curve pretty much looks complete. And I imagine if you wanted to get super precise, you could draw this many dots, but of course you won't need to do this many. Okay, so let's look at one of the polynomials we did before, x cubed plus 2x squared minus x minus 2. And I just want to readjust the window here. So as I said, this is from earlier. We had the x-intercepts of minus 2, minus 1, and 1. And sure enough, we do again. However, when you take steps of this magnitude, we're going to miss a lot of the curviness, and we can't even see the humps. So let's increase our amount of steps here from 5 to 10 and zoom in a little bit. And now let's increase that to 15 steps. And you can really see that the top of the hump here is starting to take shape. And it appears to be 1/3 away from minus 2. And the bottom of this hump seems to be at around about 1/3. So just zoom in a little bit here. Now if we zoom in to make the amount of steps equivalent to 1/6, it isn't really clear where the top of the hump or the bottom of the hump is. All right, let's zoom out a little bit again. And this gives us a better all overview of the shape. So while that perfect cube had that flattening in the middle, this has a distinctive up, down, and up again. And if we look at the negative version of this, clearly it looks like it's the same, except that it's got a down, up, and then down again. So that is the opposite of the positive version. Finally, let's have another look at that one with the square factor. So we've got that linear intercept at -1, and it's also got the quadratic at +2. And notice how we've still got the up, down, and up, but the dip sits on the axis. I'm sure you can notice that that intercept is the one that's related to the square factor. So let me give you something else to think about here. Here's a graph of a cubic, which has the same intercepts and a square factor, except that the square intercept is at -1. So once again, the square is sitting on the line, but we've still got the up, down, up for a positive. So perhaps that's something for you to think about. All right, let's go back to the OneNote. All right, so let's summarize those general shapes. So first of all, we got to describe what a positive graph is. And as far as a cubic's concerned, that's when the x cubed term has a positive coefficient. And therefore, when we have a negative cubic, it's when the x cubed term has a negative coefficient. So we've got positive and negative, and then the two basic shapes are firstly a perfect cube. And if it was positive, it would have this shape. Let me draw that again. Okay, so that's not very well drawn once again, because on the left there you can see it's sort of going straight down, and there should be a slope to it. So let me redraw that for a third time. All right, that's better. And you can see that flattening shape. And if this perfect cube was negative, it would have pretty much the same shape, but heading downwards as we go to the right. And one way to think about it is that if you looked at this point here and then snipped your graph there and flipped up the bit that's going negative, it would look a little bit like a quadratic, okay? Now the other thing about cubes are we have these humpy ones. And if it's positive, it will have a shape like this. And if it's negative, it will have a shape like this. Okay, so the key factor here with the positive is we've got this up, down, up. And for the negative, we've got the down, up, down. And just as a reminder, you're not going to learn where these humps are until next year. So this year, the focus is going to be on your X and Y intercepts. So the majority of the graphs that you'll be drawing in this lesson and for the unit will be like this: y equals x minus a times x minus b times x minus c. And that's going to have the x-intercepts obviously of a, b and c. And of course the positive one has the up, down, up. And we'll have a y-intercept of minus a times b times c. And if you push to the end of the lesson, you'll see that we've got some graphs such as y equals a minus x times a minus b squared, which has the two intercepts a and b. We've also got the down, up, down with this, but the difference being the squared intercept is sitting on the axes. And in this case, it won't take much algebra to see that our y-intercept will be minus a times b squared. Now it might be a little bit too much for some of you, so I'm not going to go through it in this video, but for those of you who want to know more, I've created this GeoGebra applet. And this will help you develop some fantastic algebra skills, because you'll see how I completely decompose the cubic function. But it's also going to help you draw an amazing cubic, because you'll be able to draw that line between the humps perfectly. Alrighty then, let's pause that video now and do the building understanding questions in the new book, which translates to questions 1 and 2 in the old book. And then you can come back and we'll get on to sketching some cubic graphs. Alright, hopefully you went well with the building understanding questions. It certainly will be a help for this section. Now let's summarize what we've covered in the introduction. We're going to be using the null factor law to find our x-intercepts. And even though we've shown you throughout this unit that you could potentially have 1, 2, or 3 intercepts, in this section, there will always be 3 intercepts. And once you've done that, you find the y-intercept by subbing in x equals 0. And then we can start with the sketching, which we do by going up, down, up for positive cubics. And of course, positive means x cubed is positive. Or we draw down, up, down when our cubic is negative. And by negative, of course, we mean there is a minus x cubed. And we focus on our 3 x-intercepts for our direction. And let me make that a little bit clearer by doing example 18, where we'll sketch the following cubics, marking in all intercepts. And our cubic in part A is y equals x plus 2 times x minus 1 times x minus 3. Now it should be pretty obvious to see I'm going to have a positive leading term of x cubed. So that will mean that we're going to do up, down and up, and that will be drawn where our x-intercepts are. And for this cubic, we can see that that's where x plus 2 equals 0, or x minus 1 equals 0, or x minus 3 is equal 0, which is the same as saying x is equal to minus 2, or x is equal to 1, or x is equal to 3. So let me paste in some axes for this cubic, and I can mark those in on the graph. So we know we're going to have an up, down, up arrows here. And of course we need to mark in our y-intercept, which is where x equals 0. So that would just be 2 times minus 1 times minus 3. So minus times a minus is positive, so we've got positive 3 times 2 equals 6. And let's mark that in on the graph. I think I'm going to do that again, because I need to make sure that I'm following these arrows, but passing through the right intercepts. So it looks like I've missed that intercept a little bit, but you know round about what I'm trying to say, okay? Of course, you don't need to draw the arrows in on your graph in fact, it'll look better if you don't. That's just me showing you how to do it now. All right, so let's just note that we don't know where that dip is, but we have made sure that we followed the up, down, up, and that fits in with the intercepts. The other thing to have a look at is that a cubic is a function, right? So we need to make sure that it doesn't fail the vertical line test. So let's just note that down. A cubic is a function, so make sure that you don't fail the vertical line test. All right, let's move on to part B, where we have the cubic y equals minus x times x plus 3 times x minus 2. And when you expand this, you'll see that the leading term, i.e. x cubed, is negative, i.e. it'll have a minus x cubed. So that means our direction at the intercepts is going to be down, up, down, which will eventually draw on these axes here. And of course, those x-intercepts are where minus x equals 0, or x plus 3 equals 0, or x minus 2 equals 0. And minus x equals 0 is the same as x equals 0, and the other intercepts are x equals minus 3 and x equals 2. Whoops, I made a mistake here. That should have been x minus 2 at the end there, which means we're looking for x minus 2 equals 0, which is obviously where x is equal to 2, not minus 2. All right, let's mark them in on the graph. I've got x equals minus 3 and 0 and 2. And we know that we want them to be going down, up, down. So we can draw the graph in something a little bit like that. Just take a note here actually that I've definitely not drawn that correctly. Because if we subbed in x equals 1, then y would equal minus 1 times 1 plus 3 times 1 minus 2. And minus 1 times 4 times minus 1 just makes 4. So y should be 4 there, but if you have a look, I've probably only got 2. But having said that, the general shape is correct. And so are all the intercepts. And that's what you really need to focus on, okay? So with that in mind, pause your video now and do questions 1 and 2 if you have the new book, or question 4 if you have the old book. Also, before class, though it's not an official part of pre-learning, it would be good if you have a look and maybe try some of the questions in the problem solving and reasoning sections in this exercise. All right, we'll see you in the summary. So as we finish this lesson off, it's important that you remember that you can't know everything about a cubic before you learn calculus next year. However, you just need to make sure that the intercepts are correct, the direction at the intercepts is also correct, and that it doesn't fail the vertical line test. I also believe that smart students will use the applets that I've created for this lesson as you try to explore and learn everything about a cubic. Alrighty, so for this lesson, a successful student will know the basic shape of the basic polynomials y equals x cubed and y equals x to the 4. Know the shape of a graph of a cubic polynomial that has 3 different factors. Be able to find the axis intercepts of a cubic graph, and know how to use the shape and intercepts to sketch the cubic graph. Alrighty, so we've made it to the end of this block of learning. So there's just one more block to go until we finish this unit. As we get to this part of the year, you can see the work is getting more and more challenging. So make sure you keep up your hard work and seek out any support that you need. Alright, we'll see you in class or the next video. Bye.